So this is going to be quick. I am just going to set the table for the very exciting things that are about to follow by giving some background on the data quality challenges in using real-world data to generate regulatory evidence. And this is going to set the stage for Claire, who's going to show an extremely exciting new tool that's going to advance our work in this area. And, well, what are we talking about when we talk about data quality? This is, real-world data. We're talking about EHR data, we're talking about claims data, registries to some extent. But the first approximation, we're talking about EHR and claims data. And the challenges with data quality for those begin with how they're collected. They are not collected for research, and consequently, there are greater opportunities for data to be missing, to be entered incorrectly, or transformed in some way that is going to distort the relationship to the things that we want to study. So that's sort of the crux of why we have a big challenge to begin with in some sense, and it's a tough one. Our ability to standardize the processes of data collection are really different than they are in research, and there's something a little insurmountable in a lot of cases. Even if you're at a research center that's attached to where the data are collected at a healthcare setting, it's not easy to really affect those processes. There's thousands of people collecting things in myriad different ways, and they're dynamic processes, so it's worthwhile to try and do that, but it's probably not realistic to expect huge amounts of change, and so that's one of the basic challenges. But one thing we can do is we can take all that heterogeneity about how things are collected, and we can represent them in a common way and in a common schema. And that, of course, is what the OMOP Common Data Model does for us so ably, and that is a huge advantage. It allows us to, well, not only standardize how we're representing data, but do that in a way that, to some degree, really standardize the meaning of things, even if they come from different sources. If my lab data are represented in a different way than yours, we can still talk about them in an equivalent way, and that's a huge advantage for generating reliable evidence from the data. Of course, that same set of structures and representations is also what allows the very talented group of coders in the community to develop the fantastic tools that we use for data characterization, for patient-level prediction, for population-level estimation. This is a huge benefit to us all. But all that goodness, all those great advantages from the CDM come at a price. It is not a trivial task to take your source data and map it correctly to all of those different ways that we need to represent them in the OMOP CDM. And so there is the opportunity for error at that stage of the process. But fortunately, there are excellent tools. This whole talk is going to talk about both the challenges and some of the solutions that have been developed and set the stage for some of the new solutions that are being put forward even as we speak. And one of those is the rabbit in the hat tool. So if you're going to do this in-house, this sort of ETL work, you're not going to hire one of the many able organizations that will do this work in a high-quality way for you, which there are several of in our community. The rabbit in the hat and white rabbit tool are a great aid, and one of the key features of them is the ability to define and execute unit tests within each part of the code. I just found out about this a few months ago. Didn't know it was there to my chagrin, and Martijn pointed it out. Martijn developed it, and unit tests are small bits of code, and they ensure that each piece of this very, very complex task of doing a transformation from your source into the CDM executes correctly. And doing that systematically is a really great practice to manage that kind of error that comes from the coding that's a part of the ETL. So there is a solution in part for that. And even though it's difficult to do, and to do that ETL work, it can be done, and it has been shown to be done. In fact, if you go to the Book of OHDSI and look in the data quality chapter that Martijn and Wojciech Husser and Claire have written, you will see the citations for several studies that really demonstrate that fact, that you can do that with minimum information loss, and it's challenging but not an insurmountable challenge. And in contrast to the data collection issues, which we don't really have a lot of power to affect, these data coding errors are things we can change, and so that's really a great area for us to focus on as a community. But even when you've done that correctly, you've done all of the mapping without error, there's still the possibility for incompatibility of things. You've got a common data model and you've done the perfect ETL, but you may not be following the same conventions. So there's more than one legitimate way to do that work. And here again, the OHDSI community has risen to the challenge, and as was mentioned earlier, there's this Themis effort, which has collected and is an ongoing effort to collect conventions for how to do that the right way, where there are equivalent ways of doing things. We settle on a convention, and you can find all of those on the CDM wiki. Let's see. And then even, well, let's say given that you've got some data errors because of how they're collected and you've wrestled with the challenges for getting them into the CDM, there's an additional challenge which just has to do with the scale of the data that are in a CDM. So it's feasible to really reckon with and get your head around the conditions and the exposures and the outcomes of a particular analysis and look at those variables and start to understand their quality at an entire CDM level. It can be very daunting. It can seem like you have this ocean of data, and characterizing the data quality for an entire CDM instance is something that's a little challenging to grapple with. And so what's really needed is some kind of organizing conceptual framework to give people a way to understand and deal with different aspects of data quality in this large space. And here again, fortunately, we have something to build on that's quite excellent. So Michael Kahn, our wonderful colleague, led a valiant group through a long process that not only consolidated each of their own separate data quality models that each had developed and created a harmonized one, they also really surveyed the entire literature of data quality in similar spaces and came up with a common vocabulary. And it's proving very useful in our particular area of doing this for big data and evidence generation. And it categorizes all the different data checks you might do at this common data model level into three broad categories. The first of which, conformance, has a pretty straightforward definition about whether or not the data in your CDM instance meets specific standards that the OMOP definitions, the OMOP common data model specifies should be there. The second is got sort of a somewhat sneaky definition. There's two different ways in which data can be complete. They can either be completely absent or present, or if they are present, they can be complete with respect to all of the things that should be there. And how plausible are they, or how believable are they? And that might seem very straightforward, but believability doesn't often have a very well agreed upon set of criteria, so that can be challenging to define. And then two of those categories have subcategories. It's probably a little mind-numbing to go through all of those. We don't need to really define them, but each of the data checks falls into some of those categories, one or another of those categories and subcategories, and can be constructed in one of two ways: through verification with reference to some internal source. So you might say a record shows that somebody has testicular cancers. In that same record for that same person, you want to make sure they're male. So that would be an act of verification for that data check. Or you can say for that person's birthday, you have that in their EHR, and you also maybe have a birthday in the tumor registry, and that's an external source, and that's called validation. So there's two broad strategies within the data quality checks in each of those categories. And so that gives you a rough sense. I just wanted to go through that very quickly of the kinds of problems that the Kahn framework organizes and the kinds of strategies that can be used to develop data checks within those categories. But even after data checks are developed and run and organized to assess the quality of real-world data source, there are other challenges, and Harlan was alluding to some of these. I'm going to recapitulate probably variations on some of what he was saying here. People bring very naturally the kind of expectations that they develop their methodological expertise within. Often that's in primary data collection, and they bring those expectations to the evaluation of quality for healthcare data in ways that are probably inappropriate, I would say. The goals of perfection probably are not realistic, given that we know data are not collected in a perfect way, and it really makes more sense to think of transparency as being the goal, very much as Harlan was saying, and transparency specifically with respect to giving people an indication where data might be missing, where they might be inconsistent, and enabling them to take action on understanding those, or where they aren't conforming to conventions. So that is the kind of tool we need, is the kind of approach we need to understanding data quality and in these data sources. And there's another slightly more nuanced point that's also worth mentioning. The FDA, in its efforts to develop the real-world evidence program, has as a goal the complete characterization of data provenance, which is always nice if you were in a position to really understand how each piece of data or all the data were collected and each stage of its transformation. That would be ideal. That's certainly a laudable goal, but it's not possible in lots and lots of different cases, especially in very large aggregated data sources that are often used. And I think it's safe to say that a lot of the work in OHDSI has established that it's really not necessary, that people are generating lots of reliable evidence without a complete understanding of provenance. So there's probably, it's useful to think about shifting our expectations there. So the real-world evidence program the FDA has developed has put forth a very broad definition of what it means by this term fit for use. That's the goal, is to understand when data are fit for use for this goal of submitting evidence that's based on real-world data for a regulatory decision. And that fit for use term basically means the fact, it captures the fact that data quality is assessed relative to a specified need. Quality, in other words, isn't a fixed feature of a data set or a data element. It only takes on meaning when it's assessed in connection with what you need the data for. So the FDA is interested in developing guidance that helps people understand how to use this evidence, how to use these data to generate evidence, and how to submit all of that to them for a regulatory decision. And they're interested in using the Kahn framework, and they see this as a two-stage process. First, evaluating the overall data source at the CDM level, and then further scrutiny at the particular analytic data set level that's relevant to the question that is being answered. And so I promised to go through that quickly. I know that was probably less dynamic a presentation than it might have been, but I wanted to just kind of get some of the basic things out there, and that's going to set up. Claire's got some really exciting things to say, and I know I'm sounding like I'm just handing it off to you, Claire, but before I do that, before I hand it over to the wonderful Clair Blacketer, who is going to give us a tour of this fantastic new solution, I want to plug, again, the chapter in the book of OHDSI, and on the one on data quality, but the entire book. I also want to note that the tutorial tomorrow on data quality is going to cover not only the data quality dashboard that Claire's about to describe, but two other really excellent tools, the PedsNet Data Quality Toolkit and the DQEC. They're both usable on OMOP data and represent a lot of excellent thought and effort. And as you would expect, the OHDSI community is so rich and so large. There's lots of other important efforts out there being done on data quality that that are not in the data quality chapter in the OHDSI book. They're not in the tutorial tomorrow. They weren't in my talk. And some of those include work that's going to be demoed later today from EvidNet. There's the work that Anthony Molinaro and Frank DeFalco have done in the Chronos tool for evaluating temporal variations that may reveal data quality problems. Ajit Lund has done really excellent work in capturing metadata about data quality that can be fed forward to users and who are using OHDSI tools. David Carnahan has been doing great work in the FDA BEST program. All folks in Eden are picking up where Martijn left off and doing fantastic work in developing support for ETL that's going to really improve data quality as well. And I am sure that there are other people doing excellent things that I have failed to mention, and I really sincerely apologize to you for that, but I am not going to stand between you and Claire any longer. So here's Claire.
Hi, good morning. I'm really actually happy to be here. I always find these few days to be extremely inspiring, and I always go home with lots of things to do and new ideas. And so One of those ideas is what I'm going to be talking to you about today. But before I jump in, I just want to revisit a little bit about what we've talked so far regarding data quality. So when we're thinking about the use of real-world data for regulatory decision-making, one of the key components really is data quality, because it can often be an obstacle to wide acceptance of the evidence that we're generating from that data. So our goal this year was to craft, an OHDSI-wide solution that would help us build confidence in our underlying data so that we might also build confidence in the evidence that we're generating. And as Andrew mentioned, the Kahn framework has really become the way in which we discuss that quality of observational health data. So we really felt that this was the best way to start when approaching a solution. And we put together this nice table of the contexts and categories. We sat there and we looked at it for a little bit, and we looked at it some more, and we're like, okay, now what? And we eventually ended up coming back to this same question over and over, which is really, what do I want to learn about my database in each place where a context and category meet? And in other words, what data quality checks do I need to write so that I can understand something about my data while still falling in line and using this Kahn framework as a guide? So in true OHDSI fashion, that led us to another question, which was, okay, how do we define data quality check? Because in OHDSI, if you haven't learned so far, we're all about transparency of communication and clarity of language. So what is a data quality check? And what we ended up deciding on, and the definition that we used, is a data quality check is an aggregated summary statistic that can be computed from the data, to which a decision threshold can be applied to determine if that statistic meets expectation. So there's admittedly a lot to unpack there. So let's just start simple, and let's just think about some of those statistics we want to compute and some of those things we want to learn from our data. So a really nice place to start, I think a lot of us start here when we start thinking about data quality. We want to look for people in our database who have funky birth years. So a lot of times this could be an incorrect number that was just input in their record. It could just be something where people sometimes get multiple birth years. So we just want to find these people and try to decide what we're going to do with them. And so this first check here is going to find the percent of records in my database where there are people having a birth year less than 1850. And you'll see it written a little bit different here up on the slide. It's written as the percent of records with a value in the year of birth field of the person table less than 1850. And admittedly, that's kind of a weird way to write that, but we did that on purpose, because when we started writing our data quality checks like this, we noticed something. These three fields here that I've highlighted, they really have no bearing on the calculation at all. That underlying statistic stays the same no matter what things I rotate in there. So what we learned is that we could actually take one singular check, like something looking for funky years of birth, and we could actually make it more generic. And we could think about CDM fields, tables, and low values, and kind of bring it up a level so that we could systematically apply it to the entire CDM, rather than thinking about it at that lower level where we would then be writing multiple checks over and over and just basically doing the same thing, but not in a systematic way. So let me give you an example of how that would work. Here, I have that same data quality check where we were looking for funky years of birth, but now I've applied it to the drug exposure table. And I'm going to find, with this data quality check now, the percent of records in my drug exposure table that have a day's supply less than 0. So I'm still using that same underlying check, that same computation calculation that we did to find those funky years of birth, but now I'm going to find these day supply values that are less than 0, because again, that's maybe something we want to take a look at and try to figure out why that's happening in our data. And then we found out, okay, if we take this one step further with this specific plausibility check, we could actually make it into something that allows us to assess plausible values for measurements in units. And I think a lot of us who have worked for a long time with observational health data, we know that measurements and units are often very tricky and very tough to assess. And so if we can do it in a systematic way, then we have a really robust solution to help us understand how well our data are representing these measurements. And for example, here's just one I took looking at hemoglobin A1C. So again, that same thing we were doing, looking at years of birth, and now we're able to look at these records of hemoglobin A1C measurements that have a value less than 4. So essentially what we've done is we've written what I like to call one data quality check, and that's that generic data quality check. And we've been able to, just in the span of a few minutes, write 3 different individual data quality checks from that one check type. So let's move on from plausibility. So those are all thinking about plausibility, and let's think about completeness. So again, another Kahn category here. So many of us, when we start on our journey through OMOP, we start mapping our data, we're getting into the ETL process. A big concern is thinking through, okay, how well have my data been mapped into the OMOP vocabulary? I think it's something that Harlan mentioned as well. You know, how well are our source values being represented as standard concepts? So this check I've written here, this is going to find for me the % of records in our condition occurrence table that don't have a standard mapping. And in other words, it's going to find those records that have a condition concept ID of 0, which is our OMOP stand-in for no matching concept. So if, again, we see the same thing that we saw with that first data quality check we wrote, where we can swap out these 2 things, condition occurrence ID, condition concept ID and condition occurrence table. We can make it more generic. We can think instead, bring it up a level, think about any CDM field or table that we want to look for standard mappings and how well that's been done, and then apply it elsewhere. So here I'm going to be looking for the % of records in the measurement table that have a unit concept ID of 0. So we've written 2 data quality check types, those generic data quality checks, and we've been able to write 5 specific data quality checks just from those 2 check types. And here's a few more examples. So this isn't all of them, but there's just a few more. So we started out thinking about the CDM specifications. So you see those like is required, is foreign key, and you'll be very familiar with that if you've ever mapped anything into the common data model. And we have a few more plausible checks there. So there's one, actually again, Harlan mentioned this, looking for plausible genders. So for example, looking for the men in our database maybe that have a record of a hysterectomy, for example. So overall, in our first version of our data quality solution, we've written 20 check types. And that may not sound like a lot, but I just want to take a second. I want you to think of a number in your mind of how many data quality checks do you think we were able to write from these 20 check types. I'm really proud to say we're actually able to write over 3,350 checks from just those 20 check types. And now you see a lot of them are in plausibility, and that's actually really thanks to Anna, Chan, and Matt. They actually sat down a couple weeks ago at Columbia, and they were able to help us define over 1,600 plausibility checks that I mentioned earlier, looking at the plausible values for different measurements and their associated units. And that's something we're really, really excited about because it really moves us forward in looking at the quality of our measurements. So thinking back to our definition of a data quality check, they are aggregated summary statistics that we compute from the data. So we've written our statistics, so let's look at some computations. So here we have those 5 checks that we wrote together and those 2 check types. And I've computed them against a large claims database, a large US database known as IBM Commercial Claims and Encounters. So you'll see they range from 0%, so I have no people in my data with years of birth less than 1850, and then they go all the way up to almost 94. So I have almost 94% of the records in my measurement table with a unit concept ID of 0. Okay, so where do we go from here? We've written our statistics and we've computed them. So again, coming back to our definition, now let's think about our thresholds. So we want to apply some threshold to these statistics to determine whether or not they meet expectation. In other words, how do we decide if these results that we've computed are good enough, which is essentially understanding the quality of our data, right? So here's what that might look like. Us as a team, we chose some thresholds that we were like, yeah, I think these thresholds might represent most of the data in the OHDSI community. So let's apply them to IBM CCAE and see how they look. So I'm actually looking pretty good. I'm passing most of them. And the way these thresholds work is that it looks at your check result, and if your check result falls at or below the threshold, you pass, and if you fall above that threshold, you fail. And my one failure is like a pretty bad failure. My threshold is at 5%, and I'm failing at over almost 94%. And when I took a look at this, I actually had a bit of an issue with it. Now, if any of you have worked with U.S. claims before, you'll know that when measurements come in, most often you're not going to see the results of those measurements. Most often we just see a record that that measurement was performed, but we're not really going to get the results of that lab or that lab value. So I know personally that in CCAE, only about 10% of the records that are going to end up in my measurement table actually have some value at all. And of that 10%, about half of those records have a unit that I could confidently map to a standard concept. So when I see this failure here, I immediately ignore it because I'm thinking, well, that doesn't apply to me. That decision threshold doesn't work well for me and for my data and what I understand about it. And what would work better for me is if my decision threshold was at a 95% rather than a 5%, based on what I know. And when I do that, I'm passing. And what I like about this is then I'm not diluting the rest of my failures. Because if I see a failure in a data quality check that I'm automatically ignoring, then it just takes away the gravity of the rest of those failures I'm looking at. It dilutes them. I'm then probably going to start ignoring a lot more of them. So what we decided was really, really important for our data quality solution was that we needed to be flexible. We needed to represent the diversity of the OHDSI community and the diversity of our data in the way that we set these thresholds. Because the thresholds that I set for my data are not going to work well for Chan in Korea. They're probably not going to work well for Nicole in Australia, and I'm certain they're not going to work well for all of our Eden colleagues that are coming on and are learning how to map their data into the OMOP common data model. So we really felt it was essential that this solution was flexible in the way that we allow these thresholds to be set. But with that flexibility comes transparency. So I can't just say, yes, I'm passing everything great, because if we're allowing everyone to set their thresholds a priori, then we need to be able to communicate that. So it's really, really important that we're not only flexible, we're representing the diversity of the community, but we're transparent and we're communicating what we've done. So thinking back to what we've talked about in our solution and the things that we wanted to include in our solution, we have our data quality check types, those 20 generic check types that we're going to be using to calculate our over 3,000 different data quality checks. And those data quality checks all need to be computed. And then we also need to set some a priori decision thresholds so that we can then understand how good those computations are once we've assessed them. So that's a lot of things we need to pack into one solution. And I'm really happy to say that we've done it. Well, us as a very large group. There's been many of us working on this. So this is just a snapshot of our GitHub. This is out here right now for anyone running an instance of the CDM. If you want to use it to assess the quality of your data, I encourage you to do so. This is our version 1. Again, we only have 20 check types, and while we've been able to create over 3,000 checks from that, there's many, many more we need to add, and we would really need a lot of input from the community to do so. So how this works is the dashboard takes a set of checks. So not only have we built in the flexibility for you to set your thresholds a priori, you can also go through and decide on the checks that you want to compute. So then there is an R program that will run them through, and then it generates an object that can then be represented in this shiny app that you see here. And our goal really is so that with this object, we could then basically package it up with any study that is being performed on an OMOP CDM instance. So not only are you getting the evidence that you're generating, but along with that, you get to see this whole data quality dashboard along with that evidence to help build confidence in what you've then generated. Okay, so I'm now going to go into a live demo, so everyone cross your fingers that it's going to work, okay? All right. Okay, perfect, it worked. Okay, so here's what it looks like so far. Oh no, it's not coming up. Oh, I have to get out of PowerPoint? That would make sense, wouldn't it? There we go. Is it coming up? Perfect. Okay. Only a slight hiccup. That's better than I thought. So here's what this solution looks like up front. So here's our Kahn table. That's the exact table that we started with. I told you we'd come back to it. So here's our table. This is for that IBM Market Scan Commercial Claims and Encounters database. And it gives you a nice overview of where you're passing and failing for each Kahn context and category. And this one's like, if we're going by US grading systems, we're at a solid B. So, if this was senior English, I'd be really, really happy right now. So the other thing I was really happy about that we built in here was some metadata about this database. So not only do we need to be transparent about the data quality, what we've computed, what those thresholds are, we also built in this way to include some metadata so you could give someone else who maybe can't speak to you or is taking this object from your study, they can at least learn a little something about your database and help them understand how that might affect the quality. So if we move down to results, I think this is the really fun part here. So what it does, it shows you a little bit of the context and categories, so you can filter by each one, which is very nice. There's a really powerful search here, so if a lot of times what I'm doing, if I just want to look at the quality checks that were run on a certain table, you can just write that table name in here and it'll pull up all those checks. So I filtered it specifically because I wanted to take a look at this one check here looking at oxygen partial pressure in venous blood. This is one of those measurements I was talking about that we've been really interested in. So it actually looks not super great. About 20% of the records with this combination of measurement concept ID and unit concept ID are failing, meaning that they have a value higher than 100. Okay, so if I click on this little plus here, I think this is really where the power of this tool comes in, and I use this all the time. So if we scroll down a little, one of the things you'll see, not only are we seeing the % of rows violated, but we get to see the number of rows violated. So we're giving you both of those numbers, and I actually really want to thank Wojciech for this, because he really pushed for this and gave a really, really good argument for why we would include this, and he ultimately was right. So thank you, Wojciech. Because looking at this at a 20%, I was like, oh man, we really got to look into this. And then there's right now only one row makes up that 20%. So it is maybe something I want to take a look at, but maybe not the first thing I want to take a look at. And when I do end up taking a look at it, I think another really great thing about what's been built here is that this tool provides you the fully qualified SQL code that was run to get these numbers. So you can take this whole snapshot here and immediately go back over to your database and run this and figure out, okay, what is the data quality dashboard pulling back that's causing that 20% number? I think this is super, super useful and something that I'm really proud to have put in here. And you'll see here too, we have our threshold. So we're communicating our threshold. So whatever you set a priori will show up here in the description. So I'm just going to show you one other example here, one I thought was really interesting. So this is an EHR data set that is from Optum. And there's this one major fail here that I just wanted to quickly show you. So this is a fail. I know it's a little hard to see, but it is looking at the number of records associated with women who have this code for a primary malignant neoplasm of a male genital organ. And there's actually a lot. So if we expand this out, it's 193,000 records of women getting this code. And it was really interesting because later on in the day, we'll hear from the Women of OHDSI group and the study that they ran. And independently, as we were developing this dashboard, we found this same issue over in the Women of OHDSI study as we did here. And so it was one night, it was Erica, Mui, and Kristen and I were all Skyping. We're like, what is this? This is really, really weird. It shows up a lot in EHR, but not so much in claims. Like, why would there be so many women getting this code? And so Erica actually ended up emailing back to Optum and was like, hey, do you have any idea of why we might be seeing this? And they had an interesting answer. So it turns out that for some reason, this primary malignant neoplasm code is associated with normal gynecological exam or routine gynecological exam for some reason. And their hypothesis is that some of those EHR, legacy EHR systems, they have a translational mechanism from ICD-9 to ICD-10. And Martin's sitting here laughing because I think he's heard this before. So what's happening is there's probably this old translation back from like 2014 or something, and that ICD-10 code got changed, but that translation never got updated in that EHR system. So it's actually really validating for us because we were like, okay, there's not something that we're doing on our end. This is actually a common EHR problem, not just in Optum, but IQVIA was seeing it too. You know, so it was a way for us to better understand what was going on here. And then it also affects our evidence, and then we can better understand our evidence, bringing it full circle. All right, so just as a couple more examples, I have one from Korea here. I've got one from Columbia University Medical Center, one from Japan, and this is just the tip of the iceberg. This is about the most I could get up before we started at 8 o'clock. I probably have like 10 or 20 more sitting that I could have pulled up. So it's super, super exciting, and I think what we've noticed really is that none of these databases are going off at 100%, and nor would I expect them to go off at 100%, because then what would be the point of us even putting this together if we were all at 100% for data quality? And so it's just really exciting because it just gives us an opportunity to learn, to dig in, to make changes, and then to better understand and add support to the evidence that we're generating. So I just have a couple final thoughts. So I just want to thank you all for listening, and I hope that you all go out to the GitHub. Please feel free to get in on the conversation. We have a lot more to add here, and we'd love all your input from everyone in the community. So just at a high level, we're taking this set of data quality check types. We're systematically applying them to all tables and fields. We're evaluating them based on the a priori set of decision thresholds that we're allowing the flexibility and the diversity within the OHDSI community to set. And then these things are all communicated through a JSON object, which can be read by this beautiful, shiny app. So I just want to say thank you. I really appreciate the support from the community this year. I especially want to thank Frank DeFalco, Ajit Londe, Pavel Grafkin, and Fatima Al-Nofal, who are all on the development team, and they did a wonderful, wonderful job. So I really, really appreciate it, and I appreciate you guys listening. So thank you.